Hello everyone, my name is Christina. I'm one of the developers of the NP³ MS Workflow, which I'm going to present to you today. So the NP³ MS Workflow is a pipeline for LC MS Metabolomics data process and analysis. It is composed of 10 major steps, where only the first one is a direct user action. So in first step, the user creates a metadata table that defining the samples that he wants to use in the job, and then the workflow proceeds from steps 2 to then, starting with a pre-processing where the MS2 data is enriched with MS1 information. Then it goes to the clustering step, followed by the quantification by samples of each final consensus spectra. Then it goes to the cleaning, which is a second clustering strategy to remove remaining redundancies. After cleaning, we have the final list of clean consensus spectra, which is identified against an in silico database from the Universal of Natural Products database. After this library identification, we go to the annotation of ionization variants, and this information is exported to a molecular network. Then we go for the merging step, where the ionization variants quantifications are aggregated to the putative M+H ions. And then we go to the biocorrelation step, and finally to the molecular networking, which the final clean consensus spectra are connected by their similarity values. We also have two visualization tools for MS1 and MS2 data, and also a command to join the library identifications coming from the GNPass platform. And the NP³ MS Workflow is a command line interface that was implemented with Node.js. It has scripts in R, Python, and C++ languages, and it's freely available in our GitHub repository. So let's take a look at what you can find in the NP³ MS Workflow repository. Alright, so here in the repository we have the NP³ MS cluster algorithm, which is used in the clustering step, and it's written in C++. We have the docs folder with a user manual. We have the rules folder with the ionization variants and rules table used by default. We have the source folder with all the scripts, and a test folder with a test dataset and some testing scripts. We also have here a template for the metadata creation and some Anaconda environments to help the user installing this platform dependencies. And the command line interface itself, which is called np³workflow.js. Here in the README, we have at the top the news of the current version. We have an overview of the pipeline, which points to the user manual, where you can find more information about what each step does. Then there is a guide for the installation with Anaconda. And then we have the getting started section, which is the section that we're going to follow here today, and when we are going to do the example of use that's present here. Here we also have then how to use section, which presents all the commands that the NP³ MS Workflow can handle. So here the way that we use to call this platform is by typing node, the np³workflow.js, followed by the name of the command and the list of options. Here at the bottom we have all the available commands for the NP³ MS Workflow, and the command we are going to use is the run command, which runs the entire workflow from steps 2 to 10. At the end, there's also a guide for the construction of a metadata table, where the user should read with attention when running this workflow for a new data set. Let's go to the Getting Started section. So here in the Getting Started section, it tells you a little bit more about the accepted data formats and ion modes. And he presents the testing data set that's present in the repository and that we are going to use in the example. This is samples from marine bacteria, and it's called L754Bax. It's present in the test folder here on the NP³ MS Workflow repository. And the first thing we are going to do is to activate the NP³ environment that you should install following the instructions present here in the README. So we have to go to the repository folder that you downloaded. Here you open a terminal window. And in this terminal window, you activate the NP³ environment. The first thing you're going to see is the NP³ tag in this new line. Okay, so let's go back to the tutorial. And here he gives us an example of use of the platform to execute the command run to process the L754Bax data set. It's passing the output name, so this is how the output directory will be named. It also passes the output path. This is where the output directory will be placed, and this is also it also passes the metadata path, the raw data path, and also it sets the tremolo identification as true and variables as 1. So let's take a look at this testing data set that's present in the NP³ MS Workflow repository. We go here in the test folder, we see the L754Bax folder, and inside it you will find the MZ.xml subfolder, which contains all the raw data files in MZ.xml format. And here we have the metadata that we are using in this example. Let's take a look at it. It's a comma separated file. Press OK. And what we have here in the metadata are the first 4 mandatory columns. We have the file name with the raw data files names. We have a unique sample code defining each sample. We have the data collection batch, which is a batch grouping where the samples that receive the same data collection batch number are grouped together. So here we have 3 batches. We have the sample types and also the bioactivity scores and 2 correlation groups. Here we also have other groupings just to test this functionality. Cool. So this metadata defines 11 samples, which we're going to use in our example. I already executed this example, so here we are also seeing the output folder where it's located, and also the pre-processing output, which named process data, and it's located inside the raw data path. And here in the pre-processing output we have a pre-processed file for each sample present in the metadata. Okay, so let's go back to the getting started section. So we can copy this command here. We go back to the terminal window. Before pasting this command, let's just take a look at the run command options. So you press node NP³ workflow run and the help parameter. This will show you a description here on the top, a description of the command and the list of options that this command accepts. Here in angled brackets we have the mandatory parameters. We have these 4 mandatory parameters for the run command, and then all the other parameters that this command accepts. So we can just paste here the command that was in the getting started sections, and the workflow would start here from steps 2 to 10. I already executed this command, so what it does is that it just prints the pre-processing statistics which shows how good was the pre-processing for this sample. You should take a look at these two variables, which are the percentage of no correspondence between MS2 spectra and MS1 retention time. With their values, you can evaluate if the pre-processing was good enough. It will warn you if there were samples with these rates above a 5% cutoff, and if that happens, you should evaluate to execute the pre-processing again to optimize its parameter values. Okay, so let's take a look to the output directory. So we come to the repository folder. Inside the test folder in the L754 bax, I have the L754 bax test folder. Inside here we have the outs folder with all the pipeline results. We have a log of run parameters with the command used to execute the run command. I'll have a copy of the metadata and of the rules table used in the ionization variants annotation. With these three files you can reproduce this job. So let's open the outs folder. Here we have some sub-clustering results, and at the end the final clustering result, which the one that we're really interested at. It is also named with the output name parameter. So let's open this folder. Here we have some clustering information. The count tables have all the quantification tables. In the identifications folder we have the results from Tremolo. In the MGF folder we have the final MGFs with the final consensus spectra. And here in the molecular networking folder we have the two molecular networks that the NP³ MS Workflow creates for you. So let's start here taking a look at the quantification tables. Here we have the quantifications from the clustering step. Here we also have the base peak intensity distribution, which the user can use to best select values for the noise cutoff parameter. And we have the quantifications from the clean step and from the merge step. The clean step is where is located our final consensus spectra, which are called the clean consensus spectra. And here we have the quantifications in terms of peak area and in terms of the number of spectra. So let's take a look at the quantifications in terms of the peak area. This is the table that also contains the correlation results. So the table with the correlation results, we have in the first lines the correlation scores that were present in the metadata table. And the correlation score of each sample is placed on top of each sample quantification column. At the beginning of the clean quantification tables, we have a unique identifier for each clean consensus spectra that's defined by row here. So the MS cluster ID is this unique identifier. We have the MZ consensus and the retention time range, and also other informations about each spectra. After the quantifications by sample, we have the samples types indicators. So we have the total quantification for all blank samples, the total quantifications for all control samples, and the total quantifications for all culture media samples, which are called beds here. These total columns can be used to remove the blank MZs, and the same for control and culture media. We also have the flag columns here that signalize possible blank or control or culture media MZs that do not necessarily appear in a blank, a control or culture media sample, but have an MZ that's closer to the MZ of a clean consensus spectra that appear in those type of samples. All right. Following here, we have the groups that were present in the metadata table. We also have the tremolo results added here as well, and the ionization variance annotation results, and then plus age candidates, which are present here in this protonated representative column, which set as ones the clean consensus spectra that were selected as an N plus age ion. Okay, so here in the clean quantification table, it's where you find the final results of the final consensus spectra. The identifications folder information is already present in the quantifications table. And here in the MGF folder, you find this MGF with a suffix of clean that contains all the clean consensus spectra resulting from the cleaning step. And this is the file that you should use to identify your data against, for example, the GNPS platform or other external tools. And in the molecular networking folder, we find the ionization variance annotation molecular network, which is the self-loop files, and also the spectra similarity molecular network, which are these two files. And here, the one in the bottom is the similarity molecular network with additional filters. We have in both we have a similarity cutoff of 0.6, and in this one we have a mean matched peaks equals 6, a topical neighbors equals 15, and a maximum component size equals 200. So let's open Cytoscape so we can visualize the information that's present in these two networks. Cool, so we have Cytoscape open here. Let's first load the spectral similarity molecular network with the filters. So we select the self loop. This is a comma separated file, so we selected the limiter here. Press OK. First we have to tell Cytoscape which is the source and which is the target node. So in the MS cluster ID source column, we select the source node. The MS cluster ID target, we select the target node. So now Cytoscape knows which clean consensus spectra he will link. We also have here the cosine similarity between these two spectra, the number of matched peaks, any ionization variance annotation when present, and their number of fragmented peaks as well. So we press OK. Let's rename this network as the spectral similarity molecular network SSMN filtered. Press OK. Here in the edge table we see all the information that was present in the self loop file, and in the nodes table we only see the name of each node, which is their MS cluster ID. So what we're doing next is that we're going to load the clean quantification table to add more information to each node and enrich our network. So you go here to import a table from file. We navigate to the clean quantification table. We select the one with the correlation. We open it. If we record, the first rows have the bioactivity scores, so we need to skip to the third row so it correctly reads the columns of this table. We are using the MS cluster ID as a key to join this information to the nodes of our network. We are importing this table as a node table, so this information is going to be attributed to each node. Alright, and we press OK here, and Cytoscape will load all this information for us. We can then add a style here, so we can see, for example, in the labels, we can see the MZ consensus of each node. So we select MZ consensus here, pass through mapping. If we zoom here, we can see this information. Oh, that's That's nice, okay? So here in the edges, you can change the width of the edges according to the cosine value. So we can make a continuous mapping here, and you see different widths depending on the cosine values, so depending on how similar are the connected nodes. Cool. And now let's load the other network, which is the ionization variance molecular network. Go to the molecular networking folder, select this annotation.self-loop. We open it. It's also a comma separated file. Press OK. We select here the source node and the target node. And it has a similar columns as the other network. We have the cosine, the annotation, the errors associated to each annotation, and the number of common samples between the connected clean consensus spectra. We're going to load this network to the same network collection. We are mapping using the shared name, which will be extracted from the MS cluster IDs in these two columns. So we press OK here, and it loads for us the ionization variant annotation molecular network. So we are calling it IVAN. Here the nodes of the IVAN are the same as the nodes of the SSMN, which are the clean consensus spectra, but here in the IVAN they are connected if they were detected as ion variants. So to visualize this information that the IVAN presents, let's label the edges with the annotation column, so we can see which ionization variant was detected. Oh, cool. And this network is a direct network. So let's put a different shape here in the target arrow, so we can visualize the direction of each link. And now we have it here. And so what we see is that this MZ was annotated as an sodium adduct of this MZ here, which was the putative M plus H ion in this annotation. Cool. We can also come here in the nodes in styling and color them according to the protonate representative information. So we can color the nodes that were selected as putative M plus H ions. We are going to color them in red. Press OK, and color the rest of the nodes in gray. Press OK. We'll see. So cool. Now we can see which are the M plus H ions and their direct ionization variants. Alright, so we have the SSMN build and the IVAN build here as well. What we're going to do next is a post-processing analysis to join the information present in these two networks. So our goal is to obtain the SSMN network with only the M plus H ions. And to do so, we are going to use the IVAN to remove blanks, and then in the remaining nodes we are going to select the putative M plus H ions and use this list of candidates to filter the SSMN and obtain only an SSMN with the M plus H ions. Okay, so let's start by removing the blanks. Here we go to the filter tool. We use to remove blanks the blanks total column. So we are selecting all the nodes with a blanks total greater or equal than 1. So this way we select all blank MZs. Then we come here in the select tool and we also select the first neighbors of the selected nodes in an undirected way. So this way we selected all the blank nodes and all the ionization variants of the blank nodes. But what we want is the nodes that are not blank, so we come here and invert the node selections. So we have all the not blank nodes selected. We create a network from the selected nodes and the selected edges. So now we have all the not blank ions. What we want to do next is to only select the M+H ions. So we use the protonated representative column here. We select the nodes with this column set to true, and we create a new network with this. Cool. Now in this final network, let's rename it. What we have is the Ivan with no blanks and only the M+H ions. And right now what we need to do is to use this list of nodes to filter them in the SSMN. And well, Cytoscape have this merge tool that we can use to make this filtering. So here in the merge we're selecting the Ivan with no blanks and only the M+H ions and the SSMN filtered. So what we want to do here is to extract the intersection of these two nodes, so of these two networks. So we'll have only the nodes that appear in both networks, and we also want to keep the links present in the SSMN. So we also have to toggle this option here so that the merge only is applied to the nodes and ignore the edges. So it keeps all the edges between the intersecting nodes. And we press merge here, and what we obtain here, let's rename, is the SSMN with only the M+H ions. Cool. Now you could proceed by analyzing your data set and looking only to the putative real metabolites that were present in your samples. I hope you liked it and that you could follow this tutorial and better understand where the information is present in the NP³ MS Workflow output. So yeah, thank you again for your attention. My name is Cristina Bazzano, and here it's all the NP³ team. It's also composed by Daniela, Guilherme, Jonas, Luiz, and Rafael. We are located in Campinas, São Paulo, Brazil, in the Brazilian Center for Research in Energy and Materials. Thank you a lot. Hope you have a good time using our platform. If you have any doubts, please feel free to come to the issues page of GitHub and leave in your comments there. Bye bye. Thank you.